All right, so now that we know something about how hydrogen atoms absorb and emit photons, let's look at some various kinds of questions that... I'm so sorry, my phone is going off here. Let's look at some different kinds of questions that can be asked, kind of variations of Rydberg questions is how I would kind of phrase this. So let's go through and analyze what's happening. We want to calculate the energy level. This already should be assigned to you that things are tough. Calculating an energy level means that we are solving for an n value. So that's what we're solving for. We want to calculate an energy level. We're going to be calculating an n. We have an electron in n equals 2. We know that it is being promoted because it is absorbing a photon. So think about what we have in our atom. We have the proton in the nucleus. We have n equals 1, n equals 2, n equals 3, n equals 4. We have an electron in n equals 2. We're giving it energy. That means that it's going to be promoted. So the new energy level that we're going to be solving for can only be something like 3, 4, 5, 6. That's what our solve is going to be. We know that our first is going to be in n equals 2. It starts at n equals 2, absorbs a photon, gets promoted to 3, 4, 5, 6, etc., etc., etc. That's what we're going to be solving for. And it has a frequency of 4.57 times 10 to the 14th hertz. So we know it's going to be a Rydberg equation, which is 1 over the wavelength of light either absorbed or emitted is equal to the Rydberg constant times 1 over n squared minus 1 over n squared. Here's the issue. We know we're going to be solving for an n. We know we have the other n. We don't have a wavelength. So you might ask, think to yourself, oh, geez, it's going to be 2 equations with 2 unknowns. It's not. The only problem that I'll ever ask you to solve, I can't say that. Most of the time, the only kind of question that I'll ask you to solve that has 2 equations with 2 unknowns is natural abundance. You actually only have one unknown in this question. The unknown that we have in this question is the n value that it's promoted to. The frequency gives you the wavelength. Remember that c equals lambda times nu. So that means that we have 3 times 10 to the 8th meters per second equals the wavelength times the frequency. So you can use the equations for the waves in order to get the other variables that you need. So in order to get the wavelength of light that is absorbed, to promote this electron from n equals 2 to n equals 3, 4, 5, we're going to take 3 times 10 to the 8th meters per second divided by 4.57 times 10 to the 14th. That gives us that the wavelength of light that is absorbed is 6.56 times 10 to the minus 7th meters. Now, we have everything we need except for the other n. So, 1 over 6.56 times 10 to the negative 7th meters equals the Rydberg constant times. Now, here's another part where it's going to get tricky. You have to be in charge of where to put the n values. So you have to keep that part of the equation positive. You can have either 1 over 2 squared, minus 1 over n squared, or you can have 1 over n squared minus 1 over 2 squared. You know it's being promoted, so that means our other n is going to be 3, 4, 5, 6. So the only way that that's going to give you a positive value is 1 over 2 squared minus 1 over n squared. That's 1/4 minus 1/9, 1/4 minus 1/16, 1/4 minus 1/25. That's the only way that you're going to get positive values. Now, again, this is half the battle. If we get to this point, you are really, really golden. But let's go through and solve for what that n value is. So 1 divided by 6.56 times 10 to the minus 7th, that is just a number. I got 1.524 times 10 to the 6th equals 1.097 times 10 to the 7th. I'm going to just leave my units out. I know I have all the right units, so I'm going to be lazy. 1 over 4 is just a number. And I'm going to leave my 1 over n squared in there. Now, be careful here. This is where I want you to resist the urge to distribute and instead divide both sides by 1.097 times 10 to the 7th. 1.524 times 10 to the 6th divided by 1.097 times 10 to the 7th gives you a value of 0.1389 equals 0.25 minus 1 over n squared. I am going to add 1 over n squared to both sides, and I'm going to subtract the 0.1389 from both sides. You get 1 over n squared equals 0.25 minus 0.1389, 0.1111. Now again, you got to get that out of the denominator. So the easiest way is to take both sides to the negative 1 power, if that makes no sense to you, the long way around. Multiply both sides by n squared, and then divide both sides by 0.111. You end up getting 1 divided by 0.1111 gives you n squared equals 9. It should be beautiful at this point in time, okay? It should be perfect. We don't actually need to worry too much about taking square roots because it should be beautiful. It should be something that makes sense. N squared is equal to 9. That means n equals 3. You should be able to do that in your head. Really and truly what you're doing is you take the square root of both sides. The square root of n squared is n. The square root of 9 is 3. It should be really, really obvious. If you get to this point and your number isn't beautiful, you, my friend, have done something wrong. So this is how you solve the Rydberg equation for an energy level. And then I gave you an added twist if I gave you a frequency instead of a wavelength. So there's one kind of variation of a Rydberg equation. Another variation of a Rydberg equation, how much energy is the difference between n equals 5 and n equals 3? I'm not going to go through and solve this. I'll just kind of give you the hint of things. How much is the energy between n equals 5 and n equals 3? You're going to use the Rydberg. 1.097 times 10 to the 7th. You're going to put the 3 in the first and the 5 in the second. You're going to go through and you're going to solve this. This is straightforward. This one's easy. We don't have to worry about getting things out of the denominator. We don't have to worry about square roots. Everything is golden. Key, we got to put the 3 in the first bite. So 1/9 minus 1/25. That gives you a positive value. You're going to solve for a wavelength. And you're going to be like, but Dr. L, it's asking for an energy. And I will say, yes, it is asking for an energy. You can get there because C is equal to lambda times nu and E equals H times nu. So you can take the wavelength, plug it into here, and solve for the frequency. And then take that frequency, plug it into here, and solve for the energy. So these wave equations go hand in hand. Knowing one property of a wave, of either a photon or of an electron, because both of them are both particles and waves, knowing one feature of it, you can get the other one. So knowing frequency, you can get wavelength. Knowing either wavelength or frequency, you can get energy. So you can know these things about these waves specifically. So again, I'm not going to go through and solve it for you. I encourage you to solve it on your own, but that's how you would do it. Solve for the wavelength, get the frequency. From the frequency, get the energy. And then last but not least, we have to what energy level? This is a hard one. Whenever it's asking for what is an energy level, that's the tricky ones. That's when you have to solve for an N. It's in the ground state, and it's going to absorb a photon that has an energy of 1.93 times 10 to the minus 18th joules. This has a lot of stuff going on in it, but again, go back to what the Rydberg equation is. What do we know? What do we not know? Well, we know is n equals 1. That's going to go in for here. We know it's going to get promoted, so it's going to go up because it's absorbing. So our n over 2, or our n, our second n is going to go over here. That's going to pop out. Or that's what our unknown is going to be. How in the world do we get the wavelength? Well, we have an energy. Energy is equal to h times nu. So we put in the energy in, we solve for the frequency, and then C equals lambda times nu. Put that frequency in, solve for the lambda. So you just got to be aware that all of these wave equations go together hand in hand. And I can give you an energy, you can calculate the wavelength. From the wavelength, you can get the frequency back and forth until you get the precise variables that would go into this equation. So again, I would start with the energy, 1.93 times 10 to the minus 18th joules. I would solve for the frequency. Put the frequency into C equals lambda nu, solve for the wavelength. That wavelength goes into the Rydberg. 1 divided by the wavelength is equal to the Rydberg constant, times 1 over 1 squared, because ground state means n equals 1, minus 1 over n squared. That would be the variable, that would be the thing that you're solving for. So here are just a few examples of different kinds of Rydberg type questions that can be asked.